In this video, we continue with our explanation of hybridization of atomic orbitals by explaining sp2 hybridization. Alright, the molecule model that we're going to be using for sp2 hybridization is ethene, or ethylene, which has the following Lewis dot structure. Okay, that is the Lewis dot structure. Now we can come up here with the SAPR theory and try to predict what the shape should be. We count electron groups, and there's 1, 2, 3 electron groups. That is a trigonal planar arrangement, and because all of the groups are bonds, then the shape around each of the carbon atoms will be trigonal planar, and we anticipate the bonds to be approximately 120 degrees. All right, so our goal here is to try to see how we can take valence bond theory and apply an orbital picture that is satisfactory, that can easily explain this structure. Okay, we go to the atomic orbital picture, and then what we see is that for carbon, again, what you expect to find is that since you have only 2 singly occupied orbitals, you expect overlaps with other atoms to emerge from these orbitals. But there's a problem with that, and that is that you would expect to find only 2 bonds, and those bonds should be 90 degrees away from each other. That's clearly not what we have right here, where we have 3 bonds, and one of them actually is a double bond, right? And the geometry is not 90 degrees, instead is planar and 120 degrees, right? So clearly, this natural orbital picture does not agree with what we see in some molecules. The question is how we can reconcile the structure that we see with the wave functions, the electronic structure of that carbon atom. Right, so the idea here is that carbon and many other atoms in the periodic table actually sometimes do not use the natural orbital picture. Instead, they have a hybridization of atomic orbitals to produce hybrid orbitals that now can explain what we see in nature quite faithfully. Right, so the hybridization that we see for this type of structure is what we call sp2, and let's try to explain how that works. Okay, so as before, you always draw here an energy diagram for this natural orbital picture, that is the 2s and these are the 2p's. Right, and then in order to be able to form more than 2 bonds, what you actually do is promote that 2s electron to one of the 2p's, and now you have the possibility to form up to 4 different bonds. Okay? Now, this is what we call the promotion step. Now what we actually do is take these single occupied orbitals and mix them, and again this is just a mathematical manipulation of the wave functions, but in this case our mixing is going to be different from what we had in the sp3 hybridization model. In this case the mixing actually is only between one of the s's and 2 of the p's, right? So notice that that will be called sp2 hybridization model, and that the way that this is resolved is as follows. Notice that because you're mixing only 3 atomic orbitals, you're going to be generating only 3 hybrid atomic orbitals, right? So again, the mixing of these 3 natural atomic orbitals is going to give you only 3 hybrid atomic orbitals that we call sp2, right? And each one of them has 1 electron. Okay? These orbitals would be 33% of s character and then 67% of p character. Now notice that there's one odd natural orbital left out, and that actually then, because it has not participated in mixing, then what we can do is just bring it to the orbital diagram and change, right? So we're going to assume that that was the 2pc orbital. Notice that this actually remains natural, right? Nothing has happened to it, and it has 1 electron. Okay, so this will be what we call sp2, the sp2 hybridization picture. Now we also have to talk about the shape of these orbitals. So the question is, well, along what directions of space are those orbitals pointing? And again, that comes from the mathematics of the mixing of the s with the p's, which we're not going to see. But what this happens to be is as follows. That carbon atom, these sp2 hybrid orbitals, actually form 120 degrees and are planar. Okay, so sp2, that would be one of them, okay, pointing towards that direction. Then another one of the 3 will be this one, sp2, okay, with one electron, and then another one, okay, comes along this direction. Those are the three sp2. Again, it's important to recognize that they're in the same plane, and the angles between them are approximately 120 degrees, right? So there's a trigonal planar structure that emerges from this sp2 combination. Now, let's not forget that this atom still has this 2pc orbital singly occupied. In this particular picture, what you will have is that that 2pc orbital will be coming in and out of the plane, okay? And that is very difficult to draw in two dimensions, so we're actually going to make it come here up and down, okay? Right? And that would mean that this is actually coming in out of the plane. Right? You also have only one electron. That is your 2pc. Right? So from here, we can then try to explain how the bonding is in ethylene. Right? Notice that here we have drawn the hybrid orbital structure for the carbon atom on the left. Then what we can do is do exactly the same thing for the hybrid orbital structure of the carbon atom on the left, on the right. Right? And what you will have is that this will be one sp2 hybrid with one electron, and then you will have an sp2 hybrid all 120 degrees from that first orbital with one electron, and then finally you will have another sp2 hybrid 120 degrees from the two, okay? And you still have the anhybrid 2pc orbital right here with one electron, okay? So clearly we can see that an overlap between an sp2 hybrid orbital of one carbon and an sp2 hybrid orbital on the other carbon gives us a sigma overlap, okay? And then we can see that the bonds with the H atoms are simply an overlap between the H1s wave functions of those atoms and the sp2 hybrid orbitals of the carbons, H1s and then H1s. Okay, and all of these are sigma overlaps, of course. And then we have something interesting right there, and that is that you still have a pc orbital in each atom coming out of a plane which are actually singly occupied, right? So they can overlap in a pi fashion, right? So there would be a pi overlap to generate a double bond. Okay, so from this orbital picture, then we can satisfactorily explain the bonding in ethylene, right? What we have is that of these two bonds that we get from the Lewis dot structure, one of them belongs to a sigma overlap between sp2 hybrid orbitals. This is a pi bond that is that emerges from pi overlap of natural 2pc orbitals, and then the bonds to the hydrogens are simply overlaps, sigma overlaps between the hybrid sp2 orbitals and then the 1s single occupied orbital of hydrogen. Okay? Something interesting about this is that again, we can go well beyond the Lewis dot structure by understanding this, the quality of those bonds. And something that is important is that once you have a pi bond, there's actually no free rotation of the molecule, right? So the presence of that pi bond means that that molecule is locked in place, and twisting the molecule would require breaking that pi bond, and that just takes too much energy, and it doesn't happen virtually at room temperature. You will need to elevate the temperature of that molecule a lot before you can actually make it rotate. Okay? That is not the case if you had a single bond, as you have in ethane, where you essentially have free rotation at room temperature because again there's no pi bond. Okay, so in this video we have continued to explain the hybridization of atomic orbitals by invoking here sp2 hybridization to explain the ethylene molecule.